Okay, so we know what to expect. If we plot a rotation curve, we measure the velocity of things rotating around a galaxy against how far out they are. If all the mass is in the middle, say a giant black hole dominated, then you expect something that looks like this. If, as seems more plausible, the mass is spread out over some radius, then you expect a velocity that's very low, then it comes up, at about where the stars run out, it then starts behaving just as in the first model. So these were the two things people expected to see when they were first able to measure rotation curves. Well, how do you measure rotation curves? If you're measuring it in the central regions where the stars are, you can use an optical telescope and take the spectrum of the stars and use the Doppler shift of the emission and absorption lines to measure how fast they're going. That's fine over here where there are stars to look at. How about further out here? Well, it turns out in places like that you normally need to use a radio telescope. Here is some footage of the Australia Telescope Compact Array, the radio telescope near Narrabri in New South Wales that I took last time I was observing there. Radio telescopes like these can pick up emission from hydrogen gas in the outskirts of galaxies and measure its velocity using the Doppler shift in the so-called 21 centimeter line of hydrogen. Using a radio telescope like this, you can see that a galaxy like M33, which appears quite small in this image, at visible light, that's where the stars are, is actually surrounded by a much larger cloud of gas, which you can pick up using the 21 centimeter emission from hydrogen gas. And you can use the Doppler effect measurements of this gas to measure rotation far out beyond where the stars are. And what do we see? Well, here's what we expected. But this is what the actual data looks like. So on the scale, the stars go out to somewhere around here. So if there was a big black hole in the middle, we would have expected something like this. We certainly don't see that. If the mass was in the form of stars, you'd expect something that goes like this, which works pretty well out to about here, but there's a huge discrepancy over there. Even when all the stars are left behind and all you're tracing is gas, and gas doesn't have much mass, the curve keeps on going up, which is very, very strange. So it doesn't match any of the predictions. It doesn't come down like this, it doesn't go up and down like that. Instead, it goes up and then stays up, or even climbs slightly, far, far out beyond where stars are happening. So if all the mass was in the center, we would expect rotation like this. Things moving very fast in here, and then slowing down, slowing down, slowing down. If, instead of having all the mass in the middle, we have a galaxy which is spread out, we get exactly the same thing, slowing down, except that right in the middle, because the galaxy mass is on all sides, it's also so slow. So slow in the middle, getting faster, and then slowing down. Those were our two model predictions. What we actually see is rather different. Here's what we actually see. Slow in the middle, getting faster as it goes out, and then staying fast. You can see the ones right out here, as far as I've put them here, these balls in the simulation, are still going every bit as fast as the ones in here. Only in the center is it slow. That's what we actually see. So what could possibly be going on here? Well, this isn't just seen in M33. Pretty much all disk galaxies show these flat rotation curves. They rise from low values in the middle, but then they keep on flat, as far out as you can measure them. So what could be going on here?